Welcome to the AP Pre-Calculus Final Review Video Solutions Guide, where I'm going to go through all 31 of the solutions. I'll go through relatively quickly, but feel free to rewind if necessary. Very first one, where we are going to be asked, on what interval am I decreasing at a decreasing rate? So just keep in mind with this, when phrasing this, my first word is going to strictly be related to the slope or rate of change. For instance, this whole section right here is obviously increasing. Because it's concave down, it would be at a decreasing rate. Keep in mind, I'm looking for the interval in this case, so I'm looking for x values. This whole section right here is clearly going down, and it is concave down, so it's at a decreasing rate. This is the section from x equals 2 to x equals 4 that constitutes my solution. If I kept going, just to kind of beat this point home, this section is clearly decreasing, but it's concave up, so this green section will be decreasing at an increasing rate. And then finally, the remaining portion here is going up, and it is concave up, so this would be increasing at an increasing rate. That's the difference between each of those four. Since I was looking for decreasing at a decreasing rate, my answer is from 2 to 4. Number 2 is asking us for really a definition here. So it's saying the difference between AROC, average rate of change, which is the rate of change using 2 points, given a start and an end point. To use the one previous, let's just say I wanted to find AROC from 0 to 6. I would go, here's my value at x equals 0, here's my value at x equals 6, and I would calculate. Well, in this case, there was no rise, and there was a run of 6, so it was 0 over 6, or my AROC over that stretch would be 0. On the flip side of this, if I want instantaneous rate of change, this is a tangent line. Let's say I wanted the instantaneous rate of change at x equals 1. I would go to x equals 1, I draw a tangent line, and I approximate its slope. Looks like I went up, roughly 2 spaces for the one that I went up. So the IROC at x equals 1 would be roughly a slope of positive 2. The big difference here, again, average rate of change is over an interval with a start and end point. Instantaneous rate of change is at one point where I simply am taking the tangent line. On which interval is my function increasing? Well, this is a quadratic, so it's going to look like a parabola, and it's been shifted 3 spaces to the right. So my axis of symmetry here is at x equals 3. Therefore, if I look at this, the entire right side of this function is going up. Everything that is x is greater than or equal to 3. The parentheses versus bracket section is going to be kind of up for debate here as we get to what is exactly happening at 3. So we're going to focus more on the endpoints than really get into the semantics of if it needs to be a opener, a bracket or a regular parentheses. On the next one, if I actually need to find the average rate of change on an interval, I'm going to go ahead and plug this in. So I'm going to pick 4 as my start point. Go ahead and plug that in. 4 minus 3 would give me 1, and I square that. 1 squared is 1. So my first coordinate, my x1 comma y1 is 4 comma 1. I'll go ahead and plug in 6 as well. I plug in x equals 6. I go 6 minus 3, or 3 squared. Once I do 3 squared, I get 6 comma 9 as my x2, y2. Now using this, that was a really ugly 2 right there. Now using this, I would plug these in. Keep in mind, what I am actually solving with is y2 minus y1 over x2 minus x1. So I'll go ahead and put 9 minus 1 over 6 minus 4, and I'll end up with 8 over 2, which would simplify down to 4 as my rate of change. From just a sheer logic standpoint as well, knowing that this is a parabola, much like this one right here, As I start moving further from the vertex, my graph is getting steeper. So therefore, I kind of already should know it's going to be the only one that's greater than +1. But that's just using multiple choice to my advantage here. Same thing on the next one. Where is my graph the steepest? Using the same logic, I have a parabola. Axis of symmetry is at x equals 3. I know the points right here, such as from 2 to 3, right there, that are close to the axis of symmetry, or from 3 to 4 are not very steep. Based on the normal 1, 4, 9 rule, I have my vertex. I go 1 space over, 1 space up, 2 spaces over, 4 spaces up, 3 spaces over, 9 spaces up. So the farther away from the vertex I am, the steeper my graph is. So I'm really just looking for which of these intervals is farthest away. So from -1 to 1, that's going to be somewhere in this region right here. But as I get to -3 to -1, I would be in this steep region right here. So therefore, the farther from the axis of symmetry, the steeper my parabola. Now I'm getting into my rational function features here. On this one, I mainly am going to be looking at a key feature here. If I know this is a vertical asymptote, that's telling me I'm expecting to see the opposite sign on the bottom. A x minus 2, not paired up. This would create a hole, so that is not going to be correct. I need an x minus 2 by itself in the denominator. C also has the same value. That would create a hole. So really A is the only option, the only one that has the denominator value I'm looking for. This also would have where I have an x minus 3, x minus 3. That would explain why I have a hole at x equals +3. While we are here, let's go ahead and explain these extra ones. These two values in the numerator that are not paired up, I flip the signs, and those are my x-intercepts. So at x equals -2 and x equals +5, I have intercepts that occur as well. So lots of different pieces there that will help me arrive at the same solution of option A. As I get to the next one, same rules apply here. This is either a nothing or a 1 right here. I know that was kind of a common hard one to read during class. However, as I look at this, I'm looking here. I have a hole at x equals -3. Keep in mind, I always flip the sign. So there is not a vertical asymptote at -3. That takes A and B out of play here. I would also, as I said, have a x-intercept, even though it's not asked, I want to remind us of this, at x equals -5, because I have that numerator value. I will have a vertical asymptote at x equals -2, still keeping C and D in play here. And then the last piece, because of the fact that these are x times x, over x times x, these are same degree functions. You have an x squared over x squared. So then I look at my coefficients. Those will determine my horizontal asymptote. So the horizontal asymptote will be y equals 1/4. Therefore, my answer is C and not D for option 7. Here's another one for the whole. This part, one that definitely worth talking about, because most of us realize the portion that repeats creates the whole at x equals -3. Obviously, all of these are still in play at this point. The y coordinate that goes along with this, keep in mind, I must find by removing this portion right here. The whole is created by that 0 over 0 and making that portion undefined right there. However, if I plug into the remaining portion right here, my -3x coordinate, the remaining piece can be solved, in which case now I can figure out what the y coordinate will be. So I'm going to have 1 times 2 over 4 times -1, which will give me 2 over -4, which will simplify down to -1/2. All right, here's another one, visual sequence of light bulbs. Which one does not give the number of light bulbs in this one here? So you're gonna have to think a little bit here as you go through. Mainly, I like to look at this and solve this here. So first just look at the number in each figure. So I've got figure 1 is 4. I've added 2 more to the next one and 2 more right there. So that looks like that's going to give me 8. The next one I've got 4, 4 in the middle, and another 4. That's going to give me 12. And then the last one I've got 5 and 5, 3 and 3, so 16. Linear growth, I'm going plus 4. So obviously I need to see a plus 4 in here somewhere. I'm kind of looking for something most likely that's going to look like that. On something like this, where each of these are a little unique, I would probably just plug in my x coordinates to see which ones work. So for instance here, these are where the figure number corresponds with an x value, and the output number of light bulbs in this case would correspond with my y value. I could take each of these coordinates and really just use them as test coordinates as it gets a little weirder with these graphs here. So if I go ahead and just plug in 1 right here, this would be 4 times 0, which is 0. This does, when I go 0 plus 4, in fact, give me the correct coordinate of 1, 4. I could do the same thing here, plug in a 1, plug in a 1. That gives me 2 times 2 is 4, plus 2 times 0 is 0. So 1, 4 does give me the correct coordinate. My next one here, this looks like it's going to be my problem because I go -4. When I plug in my 1 right there, that's going to give me -4 times, plus 4 times 3. That's -4 plus 12. So my coordinate is 1, 8. Incorrect. If I plug in a 1 here, same situation occurs. That's 2 plus 0. I should put in my plus right there. Plus 2. And that would also give me the coordinate of 1, 4. With something like this, the more weirdness going on, I like to just plug each one in and test them. Since it said which one is not the correct number, they all have their own little weird flavor to them. I just test and look for my counter example right there. Lots of different ways you could do that. That would be my method right there, where I just plug and chug until I figure out which one is going to be the outlier. Here's one as well. As you go through this and you're looking at your exponential rules, keep in mind with this is where you're taking a y coordinate times the ratio x minus an x coordinate right here. So what this means is if you know your ratio, you can just plug that straight in. Whoops, ratio. And if I know a coordinate, I can plug in my x and my y values. This basically just enables me to not have to work all the way backwards and find the y-intercept. I can, but I don't need to. When I say I can, well, I know term number 2 is 8, and I know my ratio or my multiplier is 2. So the next term would be 16. The next term would be 32. And if I go in reverse, my first term would be 4. My 0 term would be 2. So if I really wanted to, I could work backwards there, and I could go 2 times 2 to the x, and I could just know pretty much exactly what my value would be in the traditional 8 times b to the x. But then I'm going to look to plug in a value. With this, since they are using, going back here, n minus 1, come on, pen. Okay. N minus 1 right here, they are really asking us, I'm matching these up right here. Is my coordinate 1, 4? Is my coordinate 1, 12? Is my coordinate 1, 5? Or is my coordinate, come on, 1, 6? So this would be the y coordinate as my front value, and this would be my x coordinate. Keep in mind there's already a minus sign in the equation. The only one that logically makes any sense as a value in which you had 8 divided by 2 some number of times would be 4, and that would be my correct value. Again, corresponding, going back one time, to my value in my table right here. Number 11, be careful on this. This was the one that did have a typo originally. So keep in mind, if I'm doing a function composition, I'm going g of -2. So I go negative 2. My g of x value is going to be negative 3. So g of negative 2 equals negative 3. And then I'm solving for f of negative 3. I go to negative 3. I want to go to the f of x equation. That's where the little typo occurred on the original answer key. So f of negative 3 is equal to 2. Then I'm going to use the same table, but now I'm going to solve something different. F of 0. Start on the inside as always. F of 0 equals 1. So now I'm finding inverse g of 1, in which case, keep in mind, if this is the inverse, this is telling me y or g of x equals 1, in which case the question is what x value produces that coordinate. So I go to g of x equals 1 right here, and I look at what x value caused that to happen, in which case it would be negative 1. That one I got to kind of work backwards with. Here's another one. Now I'm solving for the inverse. Keep in mind, g of n is essentially y, and I'm going to, when solving for the inverse, flip these. So when I flip those, I'm going n equals the cube root of y plus 3 plus 2. As I'm undoing this, I start on the outside and work my way in. So I'm going to go n minus 2 equals the cube root of y plus 3. I'm going to undo this cube root by cubing my term right here. So I've got n minus 2 cubed is equal to y plus 3. And finally, I will undo that positive 3 right there. The last part, this y, is going to get changed back into inverse g of x, where you're telling me, hey, I solve for the inverse, and I go n minus 2 cubed minus 3. That will become my solution, and I'm just looking for the one with the proper structure, which in this case looks like B right there. All right, now I'm going to have one that is going to include some solving. This one is already kind of friendly to solve, so I can go ahead and undo some things. First of all, let's divide by 4. Divide by 4. I've got 5 to the 2x, that's a 2, I swear, equals 125. 125 is a multiple of 5 right there, or specifically 5 to some power, so I can rewrite this as 5 to the 3rd power. Anytime I can create a common base, I therefore will know the exponents are equivalent. So 2x equals 3, divide by 2, x equals 3 over 2. Again, I'm going to try to go relatively quickly with this, but if you need to rewind and go back, feel free to do so. Here's one that we see that natural log, and I know some people were freaking out today, but if these all have the same log base, the nice thing here is keep in mind with addition, this by definition is going to produce the effect of multiplication. It's like that x is going to distribute right there. So if I were to condense this, I would be looking at this right here. I'll go and parenthesize both of those. Because these are both natural log, I can therefore assume these contents must be equal to each other right here. So I can completely take that out of the picture. And now I'm just solving a quadratic. I'll go ahead and minus the 5 to this side while I'm at it. And then I'll go ahead and factor this. Oops. I'm a step ahead here. X plus 5, x minus 1 equals 0. So I flip those signs and I get x equals negative 5 and x equals positive 1. Keep in mind here, one of these is an extraneous solution. So if I were to plug negative 5 in right here, I would have natural log of negative 1, natural log of negative 5. You are never in these positions here allowed to have a negative value. That is not part of the domain of a logarithmic function. So this gets thrown out as an extraneous solution, and positive 1 is my only solution that is mathematically allowable here. All right, 16. On to 16, this is one that is quadratic. So we got to take ourselves back a step. Quadratic means they have the same second difference. So I only have really 3 consecutive terms right here. I'm going to use these. I went plus 2, plus 6. This means that I went from 2 up to 6. My second difference is plus 4. Therefore, that pattern must continue here, where I'm going to go 4 greater in this position right here to continue the second difference pattern, in which case going back the opposite direction, my values would have been 4 less. My values would have been, again, 4 less. So in doing so here, if I had 12 minus 6, W must be 6. And on the other side, if I go 12 plus 10, Z must equal 22. You will also notice in a quadratic, if this is my middle point, these points will have symmetry, which is exactly what they do have, and that's perfect. So now they ask me to go with my value of W over Z. So I have 6 over 22, each of which are divisible by 2. I will have 3 over 11 as my simplified ratio once I get there. All right, here's another one. Much easier than it seems as long as you know the language. Do we understand limit notation? As x approaches infinity, aka as I go to the right, I am approaching negative infinity. So I am going down as I go to the right. On the other side, as x approaches negative infinity, as I go to the left, I'm approaching positive infinity. So I'm looking like this. Therefore, if I'm going down on the right side, I know it is negative. And because I'm going in opposite directions, it is an odd degree. So I'm looking for one that is negative and odd. 5th power right here will do it. So 17 must be B. Same thing on this next one, based on those same rules. Again, I'll kind of go step by step with those as a reminder to us. This one, check that it's in standard form, but it goes 8th, 7th, 5th, 3rd, 1st, etc. It's in standard form, so this is the only term that matters. It is positive, and it is even. Again, I treat this as the sign tells me what the right side is doing. The degree being even or odd tells me if they go the same direction, being even, or if, like the last one, if they're odd, they go opposite directions. So therefore, I'm looking for, as x approaches infinity, as I go to the right, f of x equals infinity. And the same thing on the other side, as x approaches negative infinity, I am also going up, meaning towards infinity. So I'm looking for positive infinity, and that will be my solution. 19 is one I got a handful of questions during class, so this is one that's worth talking about here. Keep in mind, we want to go backwards. We want to go from roots or my solutions to my factors. And then with my factors, I can break it up even farther. So which of the following could be the overall equation of this polynomial? So for one, I've got a -5 as a solution, so I know x plus 5 is a solution. One thing that is very important, I have a 2i. Keep in mind, my imaginary friends are coming in pairs here, so I'm going to have a positive and negative 2i as my solutions here, in which case I will have a scenario where I attempted to take the square root of a negative. The square root of 4 would be what produces positive and negative 2i. So what this really means is x is equivalent to the square root of -4. That's how I came up with that imaginary solution. In which case, if I square this, this is telling me that I had a scenario where x squared would have to equal -4 to get that imaginary solution, or my factor itself originally would have been x squared plus 4. If these are my two values here, I can FOIL this, or since I've done so much algebra 1 along the times here, I could just keep it nicely in a box to make everything super organized here, and I would have 4x and 20. So I'm looking for x cubed, 5x squared, which is positive, 4x, which is also positive, and 20. So I'm looking for solution B as I solve number 19. That's going to be the important part, though, keeping in mind that imaginary pairs come in, or imaginary solutions come in pairs. That means you tried to take the square root of a negative, and we must work our way backwards to which factor would have created the imaginary solution. So in this case, x squared plus 4 would create the imaginary solutions of positive and negative 2i. Number 20 here, standard translation right here. So keep in mind, it is the flip it, keep it rule. If I want to go 5 units to the right towards x equals positive 5, I need to see a minus 5 inside of the brackets, or excuse me, the parentheses here. And 2 units up, it's flip it, keep it. The vertical movement is the same sign, so positive is up, negative would be down. That one is hopefully fairly straightforward, as it shows up fairly frequently on the Algebra 2 final that's coming up this week as well. On my next one here, keep in mind, I have 2 intercepts. Based on those 2 intercepts, I'm going to see an x plus 3 and an x minus 3. That's going to tell me my middle 2 solutions are not going to work. In terms of my a value, I know it must be negative, so that's going to occur with both of these. And then I'm taking my standard 149 rule into account right here. If this was, as it looks like it might be, at 0,9, let's say, if my a value is 1, I would expect the 149 rule to be in place right here. So I'd go down 1 space, meaning I'd be at 8. My next one, I'd go down 4 spaces from 9, and I would be at 2, 5. And then I would go down 9 spaces overall, in which case I would be at 3, 0, meaning this looks like my solution. If I multiplied by 1/8, this would mean that I'm having 1/8 of my expected normal movement, in which case I would be only moving 1/8 as much, meaning I would have been at 9/8. This would have been about 1. This would have been, I think, 5/8, and I would have gotten to 0. So all of those would have been much smaller numbers. Therefore, I definitely did not have an a value with some vertical shrink occur there. 22 here, this is one that, keep in mind, it is an exponential function. The rule here is every time x goes plus 1, my y value is going to go times the ratio. This is important to recognize in the pattern here. So with this, I'm looking at my y values. My y value went from 2 to 4.5. The important thing to watch out for, though, is that these are not consecutive x values. I was at 1 and I went to 3. So I did not just go 2 times the ratio to get to that value. I went ratio 1 time to get to the value at 2, 3, and then 1 more time to get to the next one. So therefore I went ratio times ratio, or ratio squared, in which case if I work this backwards, by applying the ratio 2 times, I got to a multiplier of 2.25, in which case I need to square root that and realize that the 1-time ratio is 1.5, which in this case 2 times 1.5 would give me 3, 3 times 1.5 would give me 4.5. So that's going to tell me that A and B are out as possible solutions. And then knowing this, now I can just use a coordinate, much like in the previous one, where I kind of went through a little bit of detail explaining this. I could take any of my coordinates here, but I would go y ratio x minus an x value here. So on here, since they're using this one here, this would be telling me that my y-intercept is right at 1, which does not look like the case. It looks like it's a little too high. This would be telling me that I have the coordinate 1, 2. So if I plug those in, I would plug in 1, 2, which is in fact a valid point, and my ratio, as I just figured out, was 1.5. So C would be the correct solution. Again, if I'm ever having issues, I could plug in a actual coordinate that is known. If I plug in I plug in my x value of 1, the only one from the looks of it that's going to give me the right value, or actually only ones, would be those 2. And because I know that's the wrong multiplier, I can use process of elimination to work backwards. 23 here, we're definitely getting to the calculated portion here. So this portion here, if you are doing binomial expansion, we need to keep in mind that this will be Pascal's triangle. So because this is 6th degree, I'm going to go all the way down to row 6. Keep in mind this number here is the one I'm really looking at. So I go 1, so now I'm on the right row just in time as I ran out of space. And this will be my row that matters, the bottom row that I just came up with. That will tell me my coefficients that I'm working with. Keep in mind my two values here, x and -5, those are my values. So my first term's x, my second term is -5. These are going to go one in ascending order, one in descending order. So as I use those coefficients, I'll go ahead and use a couple lines here just because I'm going to need to. I would start with 1. I'm going to start with the x term, the first term, to whatever degree I'm working with, in this case 6. The -5 would be to the 0 power, so I'm not actually going to write that. Then I will go to 6 as my next coefficient. My x term is going in descending order. I'll go ahead and just kind of write these ones first. So I go 15, x to the 4th, 20, x to the 3rd, 15, x squared, 6x, and then finally the 1 at the end would be x to the 0, so I don't really need to write that. Going the opposite direction, my -5 is going to be over here to the 6th power, and it's going to go in descending order the opposite direction. Or the other way of thinking about this is the two terms will add together to 6. So right here you have x to the 1st plus -5 to the 5th. My two exponents add to 6. Here I would have -5 to the 4th. They add to 6. -5 to the 3rd. -5 to the 2nd. -5 to the 1st. And my leading term, I don't need to write it because it's -5 to the 0, and that just equals 1. So all of those are going to explain why I got these values along the way. I would have x to the 6th. I would have my 6 times -5 would give me this -30 with x to the 5th. 15 times 25. I believe that should be a 375, since my OCD will get me there. And then the other ones I would just be multiplying out. -125 times 20 would explain this. The only thing I'm really caring about then is my x term. So what I'm really looking at will end up being this term right here. So as I solve that, what I'm really going to have is 6 to the -5 times -5 to the 5th, and my x term at the end right here. Just from a logic standpoint, I know since this is a negative value raised to an odd exponent, this will be negative. So when I multiply it by 6, it's going to be a negative and very large number. It's going to be b. If, however, since I'm just starting the calculator portion right here, I need to solve that, I would go straight on into, as they try to make me download something here and they're being annoying. I don't want to download. I'll ignore that. I would go to Desmos, and I will go 6 times -5 raised to the 5th power, and it would give me that -18,750. But again, with the beauty of multiple choice, if I knew it was a really big negative number, that would have been enough for me to be able to defeat multiple choice on my own right there. All right, so this next one here is going to have a couple of things going on as I get to number 24, where I have a logarithmic function I'm going to solve. So a couple things here. If I have this -3 in front, I'll go ahead and get rid of that to begin with. And I'm going to have log base 2 of x plus 1 is equal to 8. From here, personally, I'll probably just look at it this way. And I would say, okay, I'm going to have 2 to the 8th is equal to x plus 1. In which case, if I'm solving for x, I would go ahead and get x all by itself. 2 to the 8th power minus 1 equals x. In which case, that 1 that was subtracted away at the end was not part of the exponent. So it is answer C and not answer D right there. Another one, you could essentially just plug in a value for x, and if you do 2 to the 8th, that's going to give you 256, and that's telling you that the value inside here must equal 256. Therefore, x would be 1 less than that, or 255. All right, as we get to 25, here's one for 25.